Assalamu alaikum, hi everyone. In this video I'm going to share how to build a Newton-Raphson algorithm using Matlab programming. So this video lesson is actually the continuation of the previous video lesson with regard to the bisection algorithm. In fact, I'm also using the same problem as the example, that is the half wave rectifier with RLO that can be referred from this textbook. By the way, the Newton-Raphson algorithm is, we can say that, relatively easier as compared to bisection because it only consists of a single equation that can be seen here, but this simple equation comes at the expense of finding the derivative of the function, which is f prime beta. So let's begin with the programming. So in here, this is the set of coding for solving the problem using the bisection algorithm. So we can use the same information that we have here, the RL, omega, theta, tau, and the function are still the same. And in fact, we can use this information, the epsilon, as the stopping criteria or the tolerance, and also the maximum iteration. So this quantity AB is not relevant with our Newton-Raphsons, so no problem. But before we begin, it's better to check the Matlab workspace to see any quantity that need to be cleared, but so far this A, B, C is not related. Epsilon and the function is still being used, and then the other constant is also still being used in this Newton-Raphsons. Okay, so let's start right away. So we continue down here. So if there is any quantity or symbols that need to be cleared, so we have to clear them. But so far there is no need to do that. So we can begin with our Newton-Raphson algorithm. So maybe we can write some command to as the reference for ourselves. So this is Newton-Raphson. And at the top is the bisection algorithm. Alright. So the major difference between Newton-Raphson and the bisection, as I mentioned just now, is the derivative of the function f prime. Of course, we require the function f, but also we require the f prime for beta. So in this regard, first you have to derive by hand what is f prime. So the differentiation of sign is cos, and then exponential power negative beta over omega tau is also the exponential, but don't forget to multiply with the coefficient of beta in the power of the exponent, so we get this negative over omega tau. So we have to specify in our script the function f prime. So maybe I can enter this a little bit, so make it a little bit at the top. So f prime, so let's write f prime. So we can use the function handle to describe the function f prime. So f prime x, so x represent beta, equals to cos theta, which is q, minus, cos beta, which is x, minus theta, which is q, minus there is a few way, but I prefer to write 1 over omega times tau, which is u, so times sine theta times exponent power negative beta over omega tau, exponent power negative beta divided by omega tau. So don't forget these brackets. Okay, be careful with every single line. So now we already defined the function f prime. And then we can literally begin with the algorithm, the Newton-Raphson algorithm. So let's think a little bit. What kind of loop that we can use? Of course, while is also one option, and alternatively we can also use for loop, but I prefer to use while in this particular case. So while one means loop forever, and then we can write I equals to I plus 1 to indicates the first what do you call iteration, but before that we have to specify what is the initial value or initial guess. So before I forget, please write I equals to 0 first, and then choose an initial value or initial guess for the Newton-Raphson formula. As I mentioned in my previous video, Newton-Raphson is categorized under the open method, in which we don't require a bracket like the bisection algorithm, but we need to have an initial guess. So based on this graph, so we know that beta is located somewhere a little bit after pi. So I can use pi as the initial guess. Or you can also use some point somewhere, maybe close to 1.5 pi. But I think pi is a good choice. So this is our initial guess. Initial guess. Alright, so back into the loop. So now we can write the formula of the Newton-Raphson, which is beta I plus 1 equals to beta I minus f beta divided by f prime beta. So we don't really bother about subscript I plus 1 and I, because in the programming, when we write in this manner, x equals to x minus f x divided by f prime x, so automatically the variable on the left hand side becomes the updated value, and the right hand side is the current value. So we don't really bother about the subscript I. So then we continue with the breaking condition or stopping criteria. So similarly that we have done in the bisection, in which we use this as the stopping criteria. So maybe we can copy this and put it somewhere here, but this should be replaced with x. So as long as the value of the function of x less than the tolerance, so we can break this looping. That is actually one alternative. But I prefer the second alternative that I will show later. So, and then we can end with end. So in order to display our iteration results in the command window, we have to we have to print the value on the command window. So using the similar concept, that is the fprintf, first we can write the fprintf after this line. So after we update the value for beta and also the function, we get fprintf. So we have the I percentage 2D, and then the, I think it's better for me to copy a few lines here. So F 1 2 3. So this is for I, this is for beta, this is for f beta, this is for f prime beta. So underscore n, sorry, backslash n, and then comma, so we have this quantity I, x, fx, and then f prime x. Alright, so let's check the results on the command window. Maybe we need to put some enter to separate between the results from the bisection and the Newton-Raphson. So double enter perhaps, and then rerun the scripts. My apology. So this is the results, but I missed out listing the initial value. So I think I have to copy this and put it just before the while loop and rerun the algorithm. So I have this. This is the result for the Newton-Raphson, which is relatively faster convergence as compared to the bisection. If you want to put some header like the bisection, you can copy this again and then place this somewhere here. So now everything becomes the string, and this string, and we can remove the 0.4 because this is string, not a number, and change everything with the string, of course. So we rerun this, so we have the results. Okay, as I mentioned just now, this is one alternative. The other way to tell the iteration when you have to stop is by using x minus xo, meaning that the current value, the updated value, minus the previous value. By the way, we have to store this xo. That is before we update the value of x in this line. So first we have to store it in here, xo equals to x. So this is the value of x or beta in the previous iteration. So this is the updated beta. So by using this, so we have this kind of result. So as can be seen here, the value of x has converged to one value. So this updated value minus the previous value, if it less than this tolerance, so we break the looping. So I think that's all for now. Thanks for watching.